CSC159. The CPU and Memory. Organization, Part 2. Compiled by Fadi Abwahab. Part 2, Course Outline. This subtopic covers Introduction to Memory, Types of Memory, and Memory Hierarchy. Introduction to Memory. Also known as primary storage and main memory. Hold programs or instructions and data for access by the CPU. Made up of a large number of cells, each numbered and individually addressable. Random access. Any data located in the memory is accessible without first having to consider any other data in memory. Roles of main memory. Hold programs or group of instructions that need to be executed. Holds data to be processed by particular instruction. Stores processed data or result from instructions execution. Categories of memory. Volatile memory. Loses its contents when power is removed. Example: RAM, random access memory. SRAM, static RAM. DRAM, dynamic RAM. Non-volatile memory. Retains its value when power is removed. Example: magnetic core memory. ROM, read-only memory. EPROM, erasable programmable ROM. EPROM, erasable electrically programmable ROM. Flash ROM. MRAM, magnetoresistive RAM. Types of memory. Through the history of computing, there have been several different types of primary memory used, reflecting the technology and the system requirements and capabilities of the times. The several different types of memory are magnetic core memory, random access memory, static RAM, dynamic RAM, and read-only memory. Types of memory. Magnetic core memory. It was developed in the late 1940s and 1950s. It remained the primary way in which early computers read, wrote, and stored data until RAM came along in the 1970s. Uses a small core of magnetic material to hold a bit of data. Electrical wires woven through the core determine the magnetic polarity of the core to read the data and change the polarity by passing electrical current through the wires. It is non-volatile, expensive, and slow in operation compared to other types of memory. Types of memory. Random access memory, RAM. RAM is a temporary storage and working space for the operating system and applications. It is used to store program and user data. It is readable and rewritable, volatile. There are two types of RAM: static RAM, SRAM, and dynamic RAM, DRAM. Types of memory. Static RAM, SRAM. Considered to be a memory that has a static or stable state. Constructed from flip-flop built with bipolar transistors. The flip-flop must be triggered by a clock pulse before its static state changes. Modern system provide a small amount of SRAM that is used for high-speed access known as cache memory. Its characteristics are more expensive. Bipolar transistors tend to cost more to manufacture. Faster to access. Bipolar memories changes states at a very high speed. Require more chips. Bipolar transistors occupy more areas on an integrated circuit, IC, chip. Does not require refreshing. Types of memory. Dynamic RAM, DRAM. A volatile memory but needs more than just continued application of power to retain its information. DRAM cell depends on a capacitance to retain its logic value. This capacitance or ability to store a charge is limited. Due to small physical size of the capacitor must be recharged, refresh, frequently. Refresh action equals refresh cycle. Its characteristics are less expensive, less electrical power, smaller with more bits of storage in a single IC. Requires extra electronic circuitry that refreshes memory periodically. Otherwise the data fades away after a while and lost. Types of memory. Read-only memory, ROM. ROM is a static memory, used in situations where the software is built permanently into the computer. Example, to store operating system and math tables. Early ROM, made up of integrated circuits, IC, with fuses in them that could be blown. A blown fuses might represent a 0, an intact fuse represent a 1. Modern ROM, can be erases and rewritten. Example, EPROM, EEPROM, and Flash ROM. Its characteristics are: software is built permanently into the memory. Non-volatile, data does not change with power on or off. Not writable. Types of memory. ROM, continued. EPROM, erasable programmable ROM. This is one type of ROM which can be programmed by the user. The contents of EPROM can be erased by exposing it to ultraviolet light. EEPROM, erasable electrically programmable ROM. Another type of ROM where the contents can be programmed and erased by the user. Non-volatile, writable memory using a concept called Fowler-Nordheim tunneling. Rewriting can be done by erasing memory cells selectively, then writing new data into those cells. Flash ROM. This memory is similar to EEPROM, the way it is erased and written. The only difference is that it is faster and more flexible than EEPROM. Flash ROM can erase and write data in blocks rather than 1 byte at a time. Used in computer BIOS and devices that require faster access than a disk can offer, such as digital camera. Memory hierarchy. Memory is in fact built hierarchically, in different layers. This is because the ultimate goals in memory design are to have lots of it, gigabytes, terabytes, etc., enough to contain the entire address space. Make it fast as CPU registers, and make it affordable, not too expensive. These goals are challenging to combine since fast memory, such as SRAM, is very expensive, while cheaper memory, such as DRAM, is slower, and the cheapest memory, like hard drive storage, is extremely slow compared to SRAM or DRAM. Building memory based on SRAM only would make it too expensive though. Building memory based on DRAM only would soften the price but slow down the overall performance significantly. Memory hierarchy. To create the illusion of lots of fast memory, we create a hierarchical memory structure, with multiple levels. An example of a structure with 4 levels is shown in the figure. In the CPU, registers allow to store words, which can be accessed extremely fast. If information is not present in one of the registers, the CPU will request information from memory. First, the cache will verify whether it has the requested information available, or not. The cache is located close to the CPU and composed of a relatively small amount of fast and expensive memory, SRAM. So, if the requested information is available in the cache, it can retrieve quickly. If not, main memory, which is significantly larger and composed of slower and cheaper DRAM, is accessed. If the requested information is in the main memory, it is provided to the cache, which then provides it to the CPU. If not, the hard drive, which contains all information that is stored in the machine, is accessed. The hard drive offers a vast amount of storage space, at an affordable price, however, accessing it is slow. So, fundamentally, the closer to the CPU a level in the memory hierarchy is located, the faster, smaller, and more expensive it is. Memory hierarchy, continued. This is the detailed view of memory hierarchies based upon intended use and speed, with additional layer of input sources. If what the processor needs isn't in one level, it moves on to the next, to look for what it needs. The first three hierarchies, registers, cache, and main memory, are currently volatile memory. This means once the power is cut from them, they lose their data. The last two are non-volatile and are considered permanent storage. Registers. Typical access time, 1 clock cycle. Registers are typically static RAM in the processor that hold a data word, which on modern processors is typically 64 or 128 bits. The most important register, found in all processors, is the program counter. This tells where the next instruction is at. Most processors have a status word register which is used for decision making and the accumulator, which is used to store the result of a math operation. Complex instruction set computers usually have around a dozen or so registers since they're geared more for accessing main memory. Reduced instruction set computers have a lot more registers. Cache. Typical access time, tens to hundreds of clock cycles. Cache is also usually found within the processor, but occasionally it may be another chip. Divided into levels, cache holds frequently used chunks of data from main memory. The more times that piece of data is used, its latency when accessing it approaches cache speed. Single-core processors rarely have more than 2 levels of cache. Modern multi-core processors will have 2 levels for each core, 1 level that's shared. Main memory. Typical access time, hundreds of clock cycles. Most commonly called RAM. Main memory is relatively fast and holds most of the data and instructions that are needed by currently running programs. This used to be a precious resource up until the mid to late 2000s. Today, memory is so plentiful that modern-day operating systems will use unused portions of main memory to store the core parts of programs that are used a lot, which is also called caching, so that when opening that program, it appears to load a lot faster. Secondary memory. Typical access time, millions of clock cycles. Secondary memory is where data can be permanently stored, usually a hard disk drive, HDD, or solid-state disk, SSD. The unfortunate thing is that secondary memory has a huge gap of latency, and there's a lot of work done to close this. Aside from bandwidth performance, latency is still a bit of an issue. Removable memory. Typical access time, tens of millions of clock cycles. Data that's intended to move around resides on removable memory. Examples include floppy disks, CDs and DVDs, and USB thumb disks. The biggest drawback of course is that they're horrendously slow. Memory hierarchy, continued. The design constraints on a computer's memory can be summed up by 3 questions. How much? How fast? How expensive? As might be expected, there is a trade-off among the 3 key characteristics of memory, namely its capacity, access time, and cost. A variety of technologies are used to implement memory systems, and across this spectrum of technologies, the following relationships hold. Faster access time, greater cost per bit. Greater capacity, smaller cost per bit. Greater capacity, slower access time. Memory hierarchy, continued. As one goes down the hierarchy, the following occur. Decreasing cost per bit. Increasing capacity. Increasing access time. Decreasing frequency of access of the memory by the processor. Thus, smaller, more expensive, faster memories are supplemented by larger, cheaper, slower memories. Thank you everyone. Till we meet again in our next session. Stay safe.